I worked as a philosopher for some 25 years. I then grasped the challenge of trying to show that ontology could become a discipline in its own right, in something like the way in which psychology became a discipline in its own right in the 19th century. So for the last 10 years or so, I've been trying to create the conditions for an independent scientific discipline of ontology. And the idea would be that this scientific discipline of ontology could then be applied. So the relationship between ontology science and applied ontology would be something of an exaggeration, but it would be nice if it came true. Something like the relationship between pure mathematics and applied mathematics. So I've worked recently more and more for military related ontology projects, and all the work that we're presenting today is related to a project of I2WD, the Distributed Common Ground System Army Standard Cloud Initiative, D6A SC. And what we're trying to do is to create a system for metadata annotation within the Distributed Standard Cloud Initiative and related initiatives. And these are the leaders in the I2WD team working on these topics. So the idea in ontology, as I conceive it, is a generalization of what happened in Paris on June 22nd, 1799, when the standard meter was adopted as part of an international standard system of units. And we now have a well-established international system of units with a very well-established system of government, a well-established system of ways in which units should be referred to, so a controlled vocabulary for referring to measurement units. And this transformed science. It also made possible things like railway timetables and international air transport, because we all had the same way of measuring time and space and temperature and so on. Since the beginning of information-driven science, the need for similar standardization, generalizing from the standardization of systems of units, has become ever more evident. But unfortunately, more money is to be made from reinventing standards for each new project. So there is an incentive on the part of the people creating the support for computer-driven administration, science, government, military, and so forth, to neglect the degree to which existing standards can be reused and to create new standards. And so the ontology goal is a generalization of the goal of the metric system to try and create high-quality standards with established systems of government that will be attractive targets for reuse and will overcome the incentive that people constantly face, not just for financial reasons, but for other reasons, to reinvent wheels. What do standards give you in the ontological domain? Well, they allow multiple independently collected data sources to be viewed as if they were one data source, because they will all, in some sense, which is still to be specified, be using the same terminology standard. This means that we can do deeper analysis. It means we can do easier recovery, retrieval, search, all become easier if we have data behaving as if it had been compiled in terms of a single terminology standard or a single suite of terminology standards. Moreover, if we had this state of affairs, then we could use the same tools, the same software, the same training, the same governance for building these data stores. So we would get benefits of flexibility of personnel. We would get the benefits which science has, because everyone uses the same mathematics. You need to train people in doing mathematics only once, and they can reuse their mathematics skills in other parts of science. Now, similarly, we ought to have a core of ontology content in the use and building of which people can be trained, and they would need to be trained, ideally, only once. Now, to do that is hard, almost certainly impossible, but to do parts of it is possible, and we're already doing parts of it within the I2WD. So the most successful work that we did so far at the very beginning, a very simple pilot project, was to show that by using common terms in simple ontologies to annotate huge bodies of data within the cloud, we were able to increase the efficiency of retrieval for intelligence analysts in a way which they could recognize from one day to the next. All right. Now, one successful part of the solution to creating this state of affairs where multiple bodies of data can be treated as if they were one, this is called horizontal integration of data, turns on the use of ontologies. And I say that this is a successful part because this approach to integrating data has already been working very impressively in biology and in fields relating to biology. So we have well-established, mature ontologies with well-established, mature governance, training, and so forth in the biological world for the treatment, for instance, of genomic data. And the biologists have shown the way also when it comes to creating definitions, logical definitions of terms in ontologies, which are needed to enable high-powered software-based analysis using ontology terms. And if you look at the content of the semantic web today, which is newer than the biological ontologies that I'm talking about now, the main one being the gene ontology, then you'll see that it's still the case that practically all the high-level scientific content in the semantic web was created by the people who submitted those ontologies which had been created before OWL or RDS even existed. I think that an ontology, as is true also in the case of the International System of Units, has to live in different worlds. It has to live in the world of human beings. People have to understand what a meter is and how to describe meters or seconds or kilograms. But it also has to live in a world where people can do, it also has to work in the world of mathematics. So there have to be logical rules, which, for instance, say that every gram is 1,000th of a kilogram. We have both of those things. We have logically formalized definitions, which nowadays are standardly formalized using OWL, the web ontology language. And we have, in the biology case, corresponding English definitions so that human beings can know what they're doing when they use the ontology. So the logic doesn't necessarily have to involve the use of formal logical symbolism, but it should be compatible with what you get when you use a formal logical symbolism like OWL. All right, so it turns out that in order to make this approach work, we need to distinguish between upper-level ontologies, which organize the ontology domain, and domain-level ontologies, which are specific to particular areas, such as, for instance, artillery or intelligence preparation of the battlefield, or geology or geography or religion. So the main approach that has been adopted in the biology world has been in terms of a very careful organization, one single upper-level ontology, and then domain ontologies at lower levels, which have been created in tandem with each other so that they work well together. And I believe that that is the only way to make the ontology approach work. That is the way in which the International Standard System of Units was organized. That people were not allowed to create new systems of units for their own pleasure. Football units or BBC units or rock music units. People who wanted to create systems of units have accepted that the way to do it is to work with the organizational structure of the SI. Unfortunately, the ontology semantic web world, people have created their own BBC ontologies and their own rock music ontologies. In fact, if you look at the top, there are a dozen rock music ontologies, all of them with strange teenager names. Down here, you have the gene ontology and the protein ontology and the cell ontology. The linked open data movement, the movement which is based upon the facility of OWL and of OWL-related tools to allow people to build ontologies, because there are very few rules imposed upon people who want to become part of linked open data, the whole is not a coherent suite of ontologies It's not comparable to the International System of Units. It's more comparable to the United Nations, the General Assembly. How do we get combination of modular non-redundant ontologies? The second lecture will show how this is working to address a specific DoD directive. We're now going to describe the general approach. The suite of ontologies called the OBO Foundry, Open Biomedical Ontology Foundry, OBO Foundry. Down here, molecules, here we have cells, and then at the top we have organisms. Above organisms, we have populations. Here we have the streams, the molecules, cells. Here we have the attributes, and here we have the processes. So this is an organization of ontology modules. Now, the idea would be to have similar modules for other domains, and that's already happening. We have two suites of ontologies for military and intelligence purposes. Ron will be talking about the Air Intelligence Ontology Suite during the afternoon. The MIL portal is a site that we put in which you can visit just in order that people should have public access to some of the ontologies that we're working with. milportal.org is the address. One example, the emotion ontology, that's just one fragment of a very big ontology. And every term in the emotion ontology has a definition like this. All right, now, a few slides describe how this approach, the modular coordinated ontology development approach, has been used by the I2WD team to address the issue of horizontal integration. And actually, the main products of this work were presented at previous STIDS meetings. And you can find a page with the documentation of the work that we've done so far, including methodologies, standard operating procedures, publications, links to the collaborating project at this address. The problem that we were faced with within the I2WD work, which we're still faced with, is big data. So this is data which is big in a number of senses, not just in the number of gigabytes or petabytes that is involved, but also in the variety of the data and in the velocity with which the data changes its shape. In other words, there are new emerging threats which suddenly become important to have data about. The data is collected, but the data is collected in all kinds of strange and uncontrolled ways, so that it becomes difficult to integrate it with the existing data, which would be in the cloud stored, that is being used by intelligence analysts to address those new emerging threats. Now, I honestly believe, I started off thinking that this was a joke, but now I honestly believe that the following is true, that within our lifetimes, the military will be engaging field ontologists who will be going into battle areas and working out how to integrate the ways in which new threats are being described in terms which make the data about those new threats interoperable with the data already in the systems being used by the military. So the response times need to, given the degree to which data processing plays a role in steering the direction of the military, the response times in bringing about the needed integration have to be very short. And the issues have to be addressed by people who know what they're talking about. The idea is that as much as possible of the room for disagreement should be eliminated by the way the structure of the ontology system is built. I don't think we'll ever have perfection. I don't think we'll ever have friendly handshaking between certain groups. But we can have a lot of agreement. And this fact is proved by the way in which joint military doctrine works. So there is joint military doctrine. It's not perfect. The specific service field manuals are not completely conformant with the joint doctrine that they are supposed to inherit from, but they are largely conformant. And that's actually my preferred approach to the creation of integrated ontologies for military use. You start with military doctrine. And I'll talk a little bit about that later on. We've been working with emotion scientists, affective scientists, from a number of different schools of thought in building the emotion ontology. And we bent over backwards to try and find a school-neutral way of understanding how emotions are classified. there are quite a few universally accepted truths about certain basic emotions, surprise and fear and so on. Emotions which have early roots in our evolutionary history. And there are obviously some emotions which are more pronounced in some cultures than others and play a more important socially organizing role in some cultures than others. Shame, for instance, plays a different role in different cultures. But the way in which shame is defined is still surprisingly quite uniform. So I don't think emotions are any worse than some other things. So the general rule that we need to embrace, and I think this is a rule which is embraced by the International System of Units, for instance. It's not embraced by physicists because the interesting areas of physics are precisely the areas where science is unsettled. The general rule is you should do an ontology only if you have settled science, settled military doctrine, settled system of units. So people try to add new units to the SI, and they usually fail until the new units have tested themselves for decades within mature scientific work. So I'm not worrying about quantum physics, which I do sometimes worry about quantum physics, but today I'm not worrying about quantum physics. I'm not worried about mixed emotions. I'm not worried about hard emotions. I'm not worried about cases where we don't know what's going on emotionally, because there are going to be huge amounts of data where we do know what the emotions are and where we can use the ontologies to make the data more easily retrievable and analyzable. So the principle is low-hanging fruit. Let's do the easy part first. We need to find a way in which ontology can respond in an agile fashion to new emerging threats, or to new emerging application domains, new emerging technologies, whatever it might be. So in other words, we want to have an approach whereby we can have settled ontologies which have this nice modular organization. But the settled ontology content can be exploited to create new application ontologies for new kinds of domain entities, and in such a way that those new application ontologies will be interoperable with the existing ontologies that we've already developed and tested and used and trained with. So we need an agile way to create application ontologies. And the opposition, terminologically, we describe as one between the reference ontologies, which are the ontologies which get reused over and over again in different parts of the work that we're doing. So in biology, the reference ontologies would be the protein ontology, the cell ontology, the gene ontology, the anatomy ontology, and so forth. And then we have application ontologies, which take the portions of the reference ontologies that they need and add new content for the specific kinds of cases that the ontology is built for. So to go back to Staph aureus again, there is something called methicillin-resistant Staph aureus, which is very important. It kills people. We have the reference Staph aureus ontology, but then we have an extension for MRSA data. And because the MRSA ontology has been built as an extension of the Staph aureus ontology, all of the terms within the MRSA ontology are used in such a way that they are compatible with the use of terms in the Staph aureus ontology. It's like adding extra words to a language. So in other words, new emerging threats like MRSA should be addressed in the ontological framework, not by revising what we already have, but by extending what we already have in logical ways. And that's what we've been doing in biology now for 10 years, and that's what we need to start doing in the military. So horizontal integration, we already defined it, the ability to exploit multiple data sources as if they were one, or as if they are one. And the goal of horizontal integration, and the DoD says that this is a goal which everyone has to embrace. We need to get horizontal integration of data, is to prevent data silos and to overcome a situation where the military doctrine authors create new lexica for new kinds of warfare, so counterinsurgency, for instance, or IED detection. They create new lexicons, but they create them to create silos of data rather than creating them computationally in the way I described, so that the new lexicons would give you data which is automatically compatible with the old data. For instance, chemistry data, or data about religions, or about key leaders, or so. We need an agile strategy for extending ontologies into new areas of emerging data. This way, we embrace the incremental approach. We get good settled ontologies for data we understand, and then as we meet new sorts of data, we find ways to extend the ontologies that we already have. The solution has to have all of these things. And the precise strategy that we adopt is called semantic enhancement. Now, the idea behind semantic enhancement is again, derived from the successes that we experienced in biology. Semantic enhancement means in order to create the horizontal integration of multiple bodies of data, we are not going to have the resources to go to the original creators of the data and say, recreate your data from scratch using our preferred terminological resources. There isn't the money to do that. The people wouldn't do it anyway. A lot would be lost if we forced them to rebuild their data from scratch. So that can't be the appropriate solution. The solution has to be something like an arm's length solution, which will involve not recreation of existing legacy data, but external redescription or tagging of legacy data. And so what we do is we take the data models which are being used in the legacy data sources and in the external data sources which are being used today, and we associate the column headers in those data models with terms in the ontology, in the ontologies, which will themselves be URIs, which will point to a web page. There will be a web page for each ontology term. And then we can use the reasoning power which the ontology gives us to reason over the data within these data stores without having to amend the data stores in the way which would be required by a more radical solution. Now, it's at this point that you get problems with things like mixed emotions. If we have a data store which has data about emotion, it's likely that some of the data will be described in ways which don't correspond to our emotion ontology. Now, in the first iteration, we can just ignore those problem cases because we will have many cases which are easy to address. But then gradually, we need to work with those mixed cases, the problem cases, and find out how we can tag them. And sometimes, and this will work perhaps quite well for a mixed emotion, we tag them with two tags. So Schadenfreude would be happiness in someone else's unhappiness. We would have to tag that with some complex tag, which would include an aboutness relation. So this person is happy because of that person's unhappiness. All right, so we're going to come back to semantic impact. That's the background. We do not recreate legacy data, we tag it. Associating tags with column headers is only one part of the job. Much of the data that we need to annotate, so the technical term we use for tagging is annotating, and I'm coming to that on the next slide. Much of the data that we need to annotate will be in free text. We won't, or images. We won't have nice columns and nice data models. Even where we do have nice columns, there will be other kinds of artifacts of the way the data is organized, which we need to capture. I'm not the person to answer questions. In fact, Tanya would be perfect if she was in the room. But we do have answers to questions like that. That would be the annotations for those things. But if you have one column which is contains alphanumeric IDs and another column which contains Arabic names, then you need to have tags which tell you what those alphanumeric IDs are. But that they are alphanumeric IDs, for instance. And that's where the information artifact comes from. So there are two dimensions. There's a dimension of aboutness in the world, And then there's the dimension of attributes of the information artifact, which is about those things in the world. And we're today focusing on the attributes of the information artifact. We have annotation. That's out here. We have lots of instance level information about buildings, people, events, chemicals, factories, and so forth. And we annotate all of that information, for instance, by tagging column headers in data tables. But we also, this is really something new in our understanding. We didn't have this a year ago. And this is actually Ron Rudnicki who brought us to this recognition. We also have many legacy data dictionaries, thesaurus, lexica, doctrinal category systems, doctrinal definition lists. And all of these have been created in unprincipled or principled ways by different military and other bodies. And they all need to work together. Very, very simple example, which we actually talked about in one of the papers on the documentation page in some detail. Enhancement means enrichment. It's arm's length. It enables analytics to process the data because the ontologies come with a logical structure, and there are now many powerful tools for using that logical structure in order to analyze, search data, and in order to merge data coming from different sources. But you see, it will all work only if there is some kind of consistency between the different ontology components used.